Good morning, everybody. So, let's see. I gotta probably turn my video on. Oh, also need my camera. There I am. All righty. So, what I want to do today is I just want to wrap up chapter 5, and I'll work through the remaining few foils in the PowerPoint, and then also I'll work through some examples from the homework with y'all. Sound good? Yay! So let's start with standard editions. There's to review. There's a couple ways to do it, right? There's sort of an easy way to implement, but a hard way to analyze, which is where you simply take a standard of your known thing that you're analyzing, and you add that to your and you add that to your sample, right? Okay, I misspoke. So the way you do it is you first you measure your sample, then you spike it, and then you measure it again, right? And when you do this, that's called standard additions, right? And there's a slightly complex way of analyzing that response. Excuse me just a second. I had to sneeze. So, and the way that you can think of this is that you have a concentration of your unknown. Here we go. So you have an unspiked, just a normal analyte, right? Analyte, you know, the concentration of your analyte X in your sample is X sub I, and I indicates before spiking, right? The idea is that that is proportional to the signal, right? And then the analyte in your sample after spiking is called XF, right? And the reason it's different on the numerator and the denominator is because you've added a little spike and you've thus diluted it just a little bit. Right? And then SF is the spike, which is the same identity as X, right? This could be, if this is, say, calcium, then this is calcium and this is calcium, right? And you're ratioing these concentrations, and you're ratioing the signals. That's an easy way to do it. Slightly complicated, just algebraically, it's slightly complicated to solve for X sub I amidst all this other junk, right? Not bad. And then another way to do it is to do a constant volume approach. And the constant volume approach here is probably a little more common with instruments, you know. And in that case, you need enough sample that you can split it. Also with constant volume is the only way to do it if your instrument consumes the analyte, you know, consumes the sample when you measure it. So, and in that case, you need enough to split your specimen between, say, in this case, they used 5 flasks, right? And you add standard to 2, 3, 4, and 5, right? To 4 of the 5. You leave 1 unspiked, very important, I think. And then you dilute them all to the same volume, right? And then you plot the signal versus the spike concentration. And then the x-intercept is x sub f. That is the final concentration of the analyte in your sample, right? So this requires least squares to do it, and so I'll go through a couple of examples where we use least squares here. So you know, you can do these. If we did this, right, we add 5 mils in each flask, and x-intercept is 0.235 molar, right? Then you know, the question is, if you did this, right, that means you know the spike concentrations that you added, right? So you did all the regression. You got minus 0.235 millimolar, right? What is the concentration of X in your specimen in the sample that you partitioned here before you diluted it? Then that concentration is minus 0.235 times minus 50 over 5. So that's 2.35, right? So it goes up from 0.2 to 2 because we multiply by 5 over 50 mLs and minus 1. So that's just an example of how to do standard additions, constant volume. You take the x-intercept from the graph, and then you solve that, and then you multiply by the dilution factor is 5 to 50. So you multiply by the reciprocal of the dilution factor. So that's going to be 0.235 times 50 over 5. Right. So this is millimolar, this is mils, this is mils, mils cancel, you get millimolar, right? Good. All right. There we go. That's how it's done. Okay. So, and so let's work through this one here. Let's see if I have this guy worked it out. 1 to 25. Oh yeah, I did this one. Let's see. Okay. So in this case, I'll take down the important statistics here. We have 1 milliliter of blood diluted to 25 milliliter with spike, etc. To measure a hormone of molecular weight 373 grams per mole, and the x-intercept was minus 4.2 parts per billion. Okay, so in this case, there's two problems in series, right? And the first one is figuring out the concentration in parts per billion of the hormone, right? And the hormone here, that's 373 grams per mole, is simply minus 4.2 times 25 divided by 1, right? And then that gives you the answer in parts per billion, because this analysis was done inconveniently with parts per billion on the x-axis. The next thing to do is to convert parts per billion into molarity using this factor here. Right? That's in part 2. So let's see how we can do this guy. So we got 1 ml of blood diluted to 25, and x-intercept is minus 4.2. So the concentration of hormone in the initial thing, which is equal to x sub I, that's equal to minus 4.2 parts per billion times 25 milliliters over 1 milliliter. Okay. Because C1V1 equals C2V2 works in this case, right? So this is C1, and then V1 is here, and this is V2, and this is C2. C2 because this is what you analyzed, and you're working backwards to C1. Right? So now C1 in parts per billion, that's equal to, let's see, 25, oops, 25, 4.22 times. That's 105 parts per billion. And what we're going to do is we're going to say parts per billion is equal to micrograms per liter. So that's going to be 1 microgram per liter per part per billion, right? There we go. And then let's say 10 to the minus 6 grams per microgram. And then multiply that by the reciprocal of the formula, which is 1 mole over 373 grams. And this comes out to be 1 times 6 times, and then 373 divide. This comes out to 2.82 times 10 to the minus 7 molar, or 0.282 micromolar, or 282 nanomolar, however you prefer, whatever units you prefer there. Good morning, Alvin.
Good morning, Dr.
I feel whole again. I feel whole. Our class is extremely small today. Extremely small. We've got there's 5 by, there's only 25 of us. To
Maybe
me, that, yeah?
People have exams. Maybe, that's what I'm guessing.
Oh, I hope so. I hope it's not just because I'm screwing up as a teacher, but anyway, anything's possible here.
You got 25 of the best. That's
awesome.
That's a good way to look at it.
Awesome. I love it. I love it. Excellent. Excellent. I love it. All right. So that's and we'll do another example of that, time permitting. Right? Okay. The last general subject I wanted to touch on was internal standards, right? And in internal standards, basically, what you do is you add some weird chemical to your, in the same concentration to all of your analytes and standards, right? So you, the trick is that you're using a method that can measure both. You can measure both your unknown or your analyte and your internal standard. And so in this case, your internal standard, for example, you could take ytterbium and add it to an iron sample, right? And why ytterbium, right? Well, ytterbium or yttrium or whatever, I don't know. It's a rare earth. It's not that common. You're not expecting it to be 1 part per million or 10 parts per million in all of your samples. But so the ytterbium that's there, it's intentional, right? And you expect the ytterbium signal to be constant in each of your measurements, right? If you can measure iron and ytterbium simultaneously, then you're going to get the iron signal and the ytterbium signal, right? And you expect the ytterbium signal to be constant. The iron signal, you're not sure what's going to happen to it. Maybe it'll, go up or down or whatever, right? But if the ytterbium sample dips or increases, what you do is you assign that to drift or changes in the instrumental sensitivity to everything, right? So as an example, you could have, for example, it's really common in gas chromatography, even with an automatic injector, to get a variable amount of stuff in each injection, right? So you could take the same thing and inject it over and over, and you'll see that the amount that you analyze out, like you integrate the peaks or whatever, and you'll get a small peak, a little bit bigger peak, a much bigger peak, a little smaller peak. You get a fair amount of variation, and it just messes everything up. You can't really quantify. You can with an order of magnitude, but it's hard to quantify otherwise. However, if you add a spike of something else that you know is not there normally, and that spike is in the same concentration and everything, and what you do is that you divide the signal that you get for your sample, and you divide that by the internal standard signal. That's one way to do this, right? And by doing that, if the internal standard signal goes down, then that corrects the analyte signal, right? So for example, if the injection is poor or not reproducible, or you could take an atomic spectrometer, you're spraying this stuff into a chamber, and it's got to get all the way to the detector. And, that's not a super reliable process all the time. Sometimes there's a tiny bit of stuff that gets on the spray nozzle, and it'll clog it up slightly. And there's a lot of settings where you can't really control all of the processes as they get through the actual measurement. And in that case, it's always helpful to have an internal standard. So GC, GCMS, MS, HPLC, less so, but it still can be an issue, particularly if you manually inject. Electrochemistry, there's a lot of cases where an internal standard can help. So when we think about analyzing internal standard, here let's take this example where both the analyte and the standard have a concentration of 10 millimolar, right? I mean, this is not necessary, really. You just need to know the concentrations, right? XF and SF, right? And then you know the area or the signal that each produces, AX and AS, right? The concentrations in the signals. And that gives you a way to calculate F here, where F is the response factor. And that just pops up later, So so here's an example where we want to find the concentration of X, in this unknown. So here we have 0.08 molar X, 0.06 molar S. X is the unknown, S is the standard. They're resolvable in the experiment. There's X comes out first, then S comes out. And then the areas that come out are these guys. Right? And and this is the sample preparation, right? This is sample preparation, right? So let's make that green or something like that, right? So these are the data that are going to go in, right? Make them red, right? And then this is the sample preparation. So let's see how to analyze this guy. And this is going to be done for us here, right? The first thing we do is we compute F, right? And in this case, F is very close to 1, right? Whatever. If the If the analytes are real similar, whatever, you can get an F close to 1. And in the mixture of the unknown plus the standard, the concentration is equal to the initial concentration. Oops. Wait. Where's the fun in this one? Okay, hold on. Concentration of X. Find the concentration of X. Yeah. So you get the concentration of X here. Using F and then oh, this is using standards, and this is using our and then using our unknown. This is kind of, sorry, I didn't look this one over carefully. I apologize. But this one is you just calculate the standard in the final, right? And then using the standard in the final, you calculate X of F. Right? So let me go through that one more time here. First, you compute the response factor F, right? You're going to get F here. And then in the mixture, the concentration of S, use the response factor, right? And the dilution, right? This is S of F, right? And this is in the analyte, or the unknown, right? This is the standard, and this is the unknown, right? And then lastly, you simply you find X in the unknown, right? And so in this case, the unknown was 0.143 molar. So, gosh, this is complicated. So let me try to do this one. We'll see how this comes out. So I'll just write down these values. A sub X is equal to 423. A sub S is equal to 447. And we want to find the X, I, right? And we know that the response factor F is equal to what we got up here, which is 0.970. So we have AX over X is equal to F times AS over S, right? Make sure that's correct. 7. Yes. Okay. So so in this case, let's see, we need to know the standard concentration, right? So the standard concentration here is 0.058, 584 rather. So that would go in here. This will go in here. This will go in here. This will go in here, and we simply solve for x here. So, oops, sorry, you can't see any of that. So f here, 0.970. We got a sub s and s, and then a sub x. Right? And then we simply have to solve this for x. And so I'm just going to reduce a couple of these to numbers here, just because I'm stupid and I can't do algebra. So 0.97 AF is 447 times, and S is 0.058. 4 divide. This is equal to
0.057.
Alvin, you're messing me up. You got X already, right? 0.057, yes. But I'm still working on this.
Oh, okay, sorry.
No, he gave it up. The whole game is up. I'm just kidding.
Oh.
Let's see here. 7, 420 is AX over X. It's 423 over X, right? So X is equal to 423 over 7420, which is, let's see, hold on, I'm going to do this. 423 times is 0.056570. Is that what you got, Alvin?
Yep.
Yay! And so what are the units on this guy? This is probably, this is XF, right? This is the final concentration. I think it's probably molar, right? Yeah, these are, this is
molar.
Molar, right? And so the initial concentration will be 0.0570 times 10 over 50. So that's 0.2 times is equal to 0.0140. Okay. Yikes. Oops. No, you can't see anything I'm doing here. There we go. I have trouble. I should figure out a way to make all this go on screen or make it follow me. I don't know. Okay. So this is how to do this spike concentration thing. And it's really not that complicated. And again, in exams, we have to distill it down a little bit, you know? So I'll try to avoid any problems where we have like, to get the final concentration, that's after dilution, right?
And Dr. Terrell?
Yes, sir.
Sorry, but it's 0.01140 molar.
Oh, you're right. Yeah, it's 114. Right, thank you. Sorry. What I'll do is I'll try to not add additional, like you got to convert that to parts per billion or, you know, something like that. I'll try to make it so that there's not problems in series, you know, like so that basically we focus on individual concepts as much as possible. Okay, so let's see.
Professor, can I ask a quick question?
Absolutely, yes.
I may have missed this in the beginning. I was a little bit late. I was wondering when our next exam was.
Our next exam is hold on, let me see. I think it's in the green sheet here. Um, it's like late. It's like third week in November, I think. So it's about 3 or 4 weeks out.
Okay. Okay.
Yeah.
Sorry, I didn't mean to interrupt class. I was
No,
just
no, 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 no. That makes it's fine. That's a good question. That's a good question. So yeah, and I'll put out a notification on that subject. So that's totally fine. So all right. So again, this is one way to do it. You know, you can, and then you can also correct a multi-point calibration. You know, and in that case, you simply you can calculate the f value, right? But the main thing there is that once you get your data, is you're going to be dividing your analyte data by the internal standard data, right? So and you can so this is one way to do it is you can plot this, or rather this versus this, right? So the a sub x divided by a sub s, right? Divided by this ratio here. And the slope of this line will be f, right? And the intercept should be close to 0 here. And so I'll go through a couple of examples on that from the homework. So I don't think that I want to belabor this too much. So like I do everything else. Okay. So well, here's an example of this, right? This is a multi-point calibration, right? Where you take cadmium and you internally standardize it with yttrium. Okay, so I used yttrium in the example before, but so it's I don't want to make it seem like you always use yttrium, but you can use yttrium, right? And so this is milliliters of cadmium. This is the cadmium concentration, right? Here's the uncorrected cadmium signal, right? And the uncorrected cadmium signal versus cadmium concentration here is not great. You know, it looks pretty weird. However, if you divide the uncorrected cadmium signal by the internal standard signal here, can you guys see this okay? Maybe I should make it bigger. Maybe I should make this a little bigger. If you correct it by dividing the uncorrected signal by the internal standard signal, then that corrected concentration is in excellent linear correlation with the spike concentration added, right? And then you can, then this is for our unknown, right? This is for our unknown here. We've got these guys, and this is the formula that we're using down here. Simply divide the uncorrected cadmium signal by the yttrium signal, right? And then this guy here is the linest of this is X and this is Y. And you could actually add a trend line to this. Let's see, you can add a trend line and do a linear and display the equation on the chart, right? Just like that. You get 2.57, right? That's the same value here. And minus 0.001, that's the same number here, right? That's just a different way to get this value, right? And then in order to calculate the concentration of cadmium as analyzed here, you simply take this signal, subtract out the blank, and divide by the slope, right? This comes from y equals mx plus b. Therefore, x equals y minus b over m. So, and then before the preparation, you made note of this. It's a twofold dilution. It's 50 mils over 25. So this guy comes out to 1.52. This is from the homework. So you guys can copy this one if you want to, or hopefully, you can check your work with it. So, all right. So let me move forward here. Here's a 1-point internal standard calibration here, where and this is from, let's see, this is from, okay, here's these internal standard ones. Working backwards. This is the one we just did. This is cadmium and cadmium yttrium, right? And that came out correct, I think. And then this one is methyl benzoate. And the idea here is that a scientist wishes to measure the concentration of methyl benzoate in some sample from, whatever, by GC. And he's going to internally standardize with butyl benzoate. It's kind of hard, but it can be bigger here. So, and then, okay, the results of a preliminary run, which uses a standard of methyl benzoate and the standard butyl benzoate. This is what gives us our response factor F, right? Because we have methyl benzoate, butyl benzoate, the methyl benzoate peak, and the butyl benzoate peak, right? So this allows us to calculate F, right? And then to measure the sample, we take 1 mil of standard butyl benzoate at 2.35, 1 mil of plant stream material at an unknown concentration, and they give 481 and 408, right? Question is, what's the methyl benzoate in the plant stream in the sample? And the way to do that is here, is first we compute F, right? So here's our X value and our S value. Here's our AX and our AS. Right? So AX over X equals F times AS over S. Solve that for X, or for F rather. And this guy here comes out to 0.970. So this is F. And this is sample preparation. 1 mil of 2.1 mg per mil butyl benzoate added to 1 mil plant stream material. And we get these signals, right? And, oops, I think I have an error in my answer here. So S here is going to equal this divided by 2, right? It's 1 mil over 2 mils, right? Because the sample preparation means that we took this butyl benzoate, 1 mil of it, and added to 1 mil of the plant stream material, right? So in this case, we need to change this guy. Oh wait, no, I think I did this dilution here. Yeah. Anyway, I think that there could be a mistake in the answer here. But the idea here is that we have, we solve for x in this equation, right? First we solve for f, then we solve for x, right? And x should equal ax divided by f times s over as. So ax here is C12, right? Divided by s, or divided by f, which is B6, times the standard concentration, which is here, divided by C13, which is AS, right? And this gives us 1.22, but 1.22, this has to be multiplied by 2 here to get to xi. This is xf here, right? And then x dot I will equal f will equal this guy times 2. And this is the 2 mil, the 2 here is 2 milliliters divided by 1 mil of plant stream material. This is C1V1 equals C2V2. So there's that, and then we just gotta trim down the sig figs. Yeah, it's a 3 sig fig answer here. So 2.44 megs per mil. Okay, so that's actually correct now. I got it right somehow. So I think what I'm going to do here, guys, is I'm going to go through and I'm going to show you a couple more answers. I showed you this one. I showed you this one, right? Then there's DDT and spinach. And I will make this guy big. Right? This is how to do DDT and spinach. This is a sort of a whole deal where you've got you calculate F, and you calculate then you have the sample prep, and then you've got to do a lot of calculations here to get various things. So, but I don't have time, so I'm just going to leave this. I'll display it here for y'all. These are the formulas that you use to get things, right? In this question, strontium in teeth here. Make this guy bigger. This is the case where you, it's just a standard additions problem. And the trick here is you got to use linest to get all of the parameters. Oops. And then you can get the unknown concentration or the uncertainty in the unknown concentration here. So you get 114 nanograms per mil, plus or minus 5.6, or plus or minus 18 at 95% confidence. Basically how this guy is done. And then there's just a complicated formula for how to get the uncertainty in X from a least squares problem, where you get the line stuff back. And I wanted to show you how to do that. And there's SEY is one of the things you use from linest, 0.997. Well, you only use SEY, right? It's called SY here. Use Y bar, which is the average of those guys. Use the dev squared of X right here, which is this guy. And then there's M, and then there's N, which is 5. And then you can use the uncertainty in X in that way, right? And then the x-intercept, which is where your analytical signal is just b over m. It's actually minus b over m, and then this is again minus that. So minus times minus is positive, right? And then you can take this guy and take G11 and times G14 over G15. And then that gives you the parts per million answer. And then you can calculate the remaining statistics from that. And then here is yet another one. And I'm just gonna show this one briefly. This is for the minimum detectable concentration. This is just, you get a bunch of information. You have to calculate the signal uncertainty, et cetera. And the limit of detection problem is here. Okay, I'm over time, guys. Thank you very, very much. And I'll put this on the website so you can go back and refer to it later, should you desire to.
Was this the end of chapter 5, like the
Yes.
very end? Okay.
Yes. Yeah. I think we got to move forward here, despite
All
my
right.
stumbling lectures here. All righty.
Thank you, Dr. Chair. Have a good one.
All right.
Alrighty.
See you next week.
Thank you, guys. Thanks, Brian.
Next week.
Professor,
Yes.
I was wondering, could you also share this document in the Canvas?
I was thinking about that. Let me think about it a little bit more.
Okay.
And then maybe I'll do that. I kind of don't want to give the whole game away,
Yeah.
Because then
Yeah.
folks, like, they don't get it, like they don't do it, But maybe I'll do it this one time. Okay.
Cool.
I'll do this one.
Well, thank you.
Okay. Bye-bye.